I'm so glad that I get to talk about Kubernetes with you today. This is so much fun. Usually when we're doing Kubernetes talks, we only get, well, the stateless stuff in place, but my app is bigger than that. So let's talk about how we get the rest of the application into Kubernetes. Here's the part where I tell you I am definitely going to post the slides of my site tonight, but that's never worked out for me either, which is why you can go to robrich.org. Let's head there right now. And you can click on presentations here at the top. And here's building stateful workloads in Kubernetes. The slides are online right now and getting posted to chat right now too. While you're here on robrich.org, let's click on About Me and learn about some of the things that I've done recently. I'm a Microsoft MVP, a Docker captain, and a friend of Redgate. AZ GiveCamp is really fun. AZ GiveCamp brings volunteer developers together with charities to build free software. We start building software Friday after work. Sunday afternoon, we deliver the completed software to charities. Sleep is optional, caffeine provided. If you're in Phoenix, come join us for the next AZ GiveCamp. Or if you'd like a GiveCamp near you, hit me up on email or Twitter, and let's get a GiveCamp in your neighborhood too. Some of the other things that I've done, I do a lot with Docker and Kubernetes. So if you have a need for training or consulting, hit me up. One of the things that I'm really proud of, I replied to a .NET Rocks podcast episode. They read my comment on the air and they sent me a mug. Woohoo! So there's my claim to fame, my .NET Rocks mug. So let's dig into building stateful workloads with Kubernetes. We talked about this guy. As we look at stateful workloads, let's first start with stateless workloads. So in stateless workloads, we have a pod, there's a container inside, we'll probably scale our pods using a deployment. We have a service that load balances in front of it. We've got an ingress in front of that. And users then resolve DNS to the ingress resolves to the service load balances across the pods that forward to the containers. Yeah, we got this. That's the end of our Kubernetes 101 talk, but our application is a little bit different than this. Our application probably looks like this. Now in this diagram, we have a few more moving pieces. On our ingress controller, we have SSL termination. We have a certificate. We also have a domain. Our pods may need to connect to a database. It needs the username and password to do so. Our database probably needs to scale up so that it's horizontally scaled as well. We need to save files, and we need to know where those files are on disk. Maybe we need to authenticate to them. Now here's a stateful application inside of Kubernetes. How do we do this? That's what we're going to dig into today. We're going to dig into all of the stateful pieces of Kubernetes to be able to put the rest of the application into Kubernetes. So let's talk about state. What is state? These are not the states that we're talking about today, but these are indeed states. We're going to talk about state. State is things that live beyond the current lifetime. So if my current lifetime is a function, then the state will be something that lives beyond the function. Maybe it's a class variable. Maybe our lifetime is a request and response. So we want something that will live beyond that. So let's push some data into the database. Or maybe the state is beyond a server restart. So if we save our logs on disk and the server reboots, we need to make sure that we still have logs. These are state, things that live beyond the current request or the current lifetime. So as we dig into Kubernetes, we'll take a look at these types of stateful resources. We're going to take a look at configuration, secrets, data stores, file stores, and singleton services. Let's double click into singleton services and take a look at how that works. Well, singleton services, I need to collect the entirety of the state of the system to be able to make a decision. For example, a month-end report, I need to collect the entire month's data, not just a few days or this department. I need all of the data to build that report. Or a primary key. Now, if we have an auto-incrementing primary key, we need to have exactly one thing that hands out the next auto-incremented primary key. If we had 2 or 3 or 5 nodes all doing this, then they would collide. So how do we build these stateful singleton services on top of an inherently stateless, auto-scaling, auto-restarting Kubernetes service. So those are the types of state that we're going to look at: singleton services, file stores and data stores, secrets, and configuration. First off, a note about kubectl get all. kubectl, kube control, kubectl, that control the command line that we use for accessing Kubernetes. When we say kubectl get all, we don't get all. Instead, we only get stateless resources. Now, as you grab these slides from robrich.org, you can click through to each of these blue links to learn more about the details behind each of these issues. Each of them are questions about, well, when I say kubectl get all, I don't get all. Yeah, you're right. They very specifically designed kubectl get all to only return the things that you could delete and recreate without altering. So by definition, stateless resources. Anything that you could delete and recreate and not get exactly back to the thing that you had won't be shown in all. So any volumes, if we're deleting files, we can't recreate that. So volumes aren't shown in kubectl get all. So how do we get, well, everything? Here's a really cool script, and this awk script is just on and on. So I create a shortcut for this, an alias, but you can get at the specifics for this inside of this issue, or you can just select this text and paste that into your own alias. What we're doing is we're creating this command, kubectl API resources, that will return a list of all resources inside of the system. Now, this includes custom CRDs. So if you have a CRD for Istio or for another system, then you'll get those resources as well. So let's do a kubectl get resources. We'll pipe it to awk to go grab the first piece of that. We will grep out the header. We probably could have done that in awk as well. Then we'll pipe that to zargs, pipe that to sed to replace space with comma. Now we have a comma delimited list of all the resources in the system. And we are going to say kubectl get that list. And now because we have a comma delimited list of all the resources, we get all the resources. Much like if you did kubectl get pod, comma deployment, comma service, comma ingress, you would get all those resources. We're just building up the list of every resource in the system. So if you really want to kubectl get all, then here's the script to be able to pull that off. But as we dig into some of these stateful things, know that if you do a kubectl get all, you won't get those too. So there's the punchline. kubectl get all isn't actually all the resources, and that's okay. So first up, let's talk about volumes. Now in Docker, we talk about volumes as symlinks into the container. And in Kubernetes, volumes work pretty much the same way. We provision them slightly differently, but that's in effect the same mechanism. We want a specific folder inside of our container to actually not live inside the container, but rather to live on a more durable storage space, perhaps a SAN or a cloud host, maybe Amazon S3 or Azure Blob Storage. Here's where we put files that we need to live beyond the lifetime of the pod. If the pod restarts and we've saved data to that pod's file system, then, well, that content is gone. Now, an interesting gotcha here is that we're symlinking a folder into place inside that container. The container doesn't really get that that folder isn't just part of the natural file system. So when it creates file system locks on that particular file, it's creating locks on that image's file, not the file in the original resource. So that means if two containers connect to the same volume and they both have write locks on that file, they'll both continue to write to that file. File locks don't work in volumes. That's just the nature of symlinking in distributed file system. So how do we create a mechanism where we can link in this volume into place inside this container? Now here's a pod definition. Maybe this pod definition is part of a deployment, or maybe it's a separate pod. We have our standard API version and kind, our metadata, our container section. And then we have a bunch of details about how this container works. So for example, the image, the name, maybe we have other details. And then here's that volume mounts section. Here in the volume mounts, we specify the path inside the container that we want to symlink into, and we give it a name. So in this case, I'm calling it the volume. Here in this volume section outside of the containers, we now say, what is that volume? So here, the volume, we're using the host path driver to create a folder on our host. Now, host path will create a folder on that particular host, but this isn't super durable as well. If I have a multi-node cluster, then this is only on that one specific node. What if that node has problems? In development and for single node clusters, host path is perfect, which is why I'm using it here. But if you're using this in production, you might want to use a different driver. Maybe pipe it out to Azure File Storage or EMS on S3. But for development and testing, host path is perfect. You can just grab this from robrich.org, copy and paste it, and take a look at it. So we've mapped this host path into this container directory. Our application can just read and write files inside of this path as if it was local to the pod, but the data is actually stored over here in a more durable space. If our pod restarts and we remap that content, then we still have all those files that we saved in place. Great. This pod definition could be part of a deployment, or it could be part of just a standard pod. So now we do have a dilemma. Who owns this? Should the developer own this pod definition? After all, the developer specified the image name and the version, the label. Or should operations own this? After all, operations is the one that mapped the path to very specifically ensure this folder is backed up and it's using a durable mechanism. So who owns this file? Well, maybe developers own the top half and operations owns the bottom half and merge conflicts. And yeah, if we have a separation between dev and ops in our organization, who owns this? Well, let's take a look at a built-in Kubernetes mechanism for being able to support this separation between development and operations. Let's create some storage. Now, in this case, I've shown it as a hard drive icon, but we could think of this maybe as NAS. And so we'll have this storage. We'll carve it up into little pieces. So we'll call each of these a persistent volume. Now, each of these pieces, in this case, I've shown them all as the same size, but they don't need to be. So now let's take one persistent volume and let's claim it. And we'll claim that volume and attach it as a volume into our container. We have storage, we have persistent volumes, we have persistent volume claims, and then we map that volume into place in our container. Now, the beautiful thing here is that we have this natural separation here between what operations owns and what development owns. Development can own the persistent volume claim and all the details that they need to be able to map that volume into place, where operations can own the persistent volume and how that's stored on disk to ensure that it's authenticated correctly and backed up correctly. That's built into Kubernetes so that we get this really elegant separation between dev and ops. Let's take a look first at a persistent volume. So we've taken one of those chunks of our storage, and we're defining how that chunk works. So API version v1, kind persistent volume. We can give it the standard name and labels, and then we give it a storage class name. Now, in this case, it's manual. We give it a capacity, so we've got 10 gigs. And we have access modes. We have read write once, we have read write many, and we have read only. Now, this is great. We can give different read and write permissions to this. If we have read write once, then one pod can write to it and no other pod can write to it. Then we also define that host path and the path to the directory. So maybe this is Azure Files or S3. In this case, we're still mounting it to that same directory on the host. So we've defined the criteria of this small chunk of storage. It's going to be 10 gigs. It's going to be read write once, and a storage class name manual. Next, let's take a look at the persistent volume claim. Now, the persistent volume claim matches on those three criteria: the storage class name, the access modes, and the storage needs to be this or greater. So in this case, storage class name of manual, access mode, read write once, and the storage of 3 gigs, that matches that persistent volume. And so we can choose to claim that persistent volume for this pod. This is a persistent volume claim. So now the developer has identified the details that they need. And then let's map that into place in our pod. So our container definition is identical. We have that mount path into the directory. We give it a name. But down here, as we're defining what that name means, instead of host path, we're saying this is a persistent volume claim. And here's the claim name. So this persistent volume, this path in the container is mapped as the name volume. That's a persistent volume claim. Here, PV claim. Here's the PV claim, and it claims a particular type of storage. This one happens to match, that is PV volume. And so now we have that piece that allows us that great separation. We created a persistent volume, carving up the storage. We claimed one of them that had the exact match of access mode, storage class, and at least that much storage. And we symlinked that into the pod. Now that's perfect. If you noticed carefully, this one asked for 3 gigs, and the volume was 10 gigs. It matched because it was 3 gigs or better. That's great. So we don't have to be really precise on the storage needs. We just need a persistent volume that is at least as big, matches the access modes and the storage class name. And we get that nice separation. Now, inside the container, it's just writing files into a directory. It just happens to know that that directory is the magic spot. And those files get written into storage where ops can ensure that they're backed up and versioned correctly. And then developers can ensure all of the details about what they need to be able to connect. That was great. We were able to get durable storage where beyond a pod restart, we can get our files back. If we're uploading, say, profile pictures or import files, we can save them into a volume to make sure that they're durable, that they're stateful beyond the current request. Next, let's take a look at configuration. Config maps. Configuration is a read-only mechanism for specifying config details. We can mount them either as volumes or as either as environment variables or as volumes files. And so let's take a look at doing that. Now here's some configuration built into our pod. Now we might have other details. Maybe we have a volume definition. We've identified the container name. Maybe we have resource limits. And then we have an environment section that specifies the environment variables. So in this case, I have an environment variable called the message, and its value is hello world. I have an environment variable called foo, and its value is bar. So inside my application can just take a look at the environment variables that it has available to it, read that environment variable, and get the configuration details. Now, who owns this? Should the developer own it? Should operations own it? Maybe developer owns the top half and operations owns the bottom half. Is there a built-in mechanism where we can separate these out so operations can own one and developers can own the other? Yes, built in, we have a config map. Now here in a config map, we have a list of settings. So we have the name and value of various keys in our config map. Now, here's the name of our config map. It is the config map, and we have a key secure database, value of Cyril. Key of logging secures value of true. And so each of these key and value identifies the various details inside this config map. The name then groups all of those config values together into one spot. Now, how do we map this into place? Let's first map our config map as environment variables. Here in our container definition, we say environment from config map reference, and we give it the name of that config map. Now, the cool part here is that we don't need to enumerate all of the keys inside of our config map. It'll just pull them all in. Now, there definitely is syntax if we do want to enumerate them, but in this case, I chose to just say, I want to grab them all. So any configuration inside that config map will end up as environment variables inside my pod, inside my container. Next, let's take a look at files. Now, we could do an env and from in the same way, but let's enumerate each of the config keys that we want. So here I've got some volume mounts, and you'll notice that this syntax is exactly the same syntax as when we're doing storage volumes. But as we define what this volume is, we're not using host path or a persistent volume claim. Instead, we're saying this is from a config map, and we'll give it that config map. So if my application enumerates all of the files in this directory, it will see those 3 file names. It'll be able to open each one and be able to read the contents of that file to get the value of that configuration. So that was excellent. We were able to map in configuration into our application, keeping that configuration separate. Now our developers can keep the pod definitions, operations can keep the config map, and those config maps then can be different between different environments, as long as we have the same keys in each one. Now, if we don't have that separation between dev and ops within our organization, we can use the simple approach of just putting it in the pod definition. But when we need that separation, we can easily upgrade to separate config maps and pod definitions. Now, what if some of these values are secret? What if we need to keep them, well, safe? Username and password or API token. We have secrets. Now, the interesting thing about secrets is that they are not encrypted at rest by default. Starting in Kubernetes 1.13, we can choose to encrypt them at rest, but we need to turn that on. So are they secret if they're just not secret? They were actually base 64 encoded before 1.13, and so that's a little scary. Now that each of these secrets needs to be on every node in the cluster. In case a pod gets scheduled on that node, it needs to be able to read that secret. So if we lose a node in our cluster, then we should probably consider those secrets lost and rotate the keys. How would we create a secret? Now, we can definitely create it through YAML, and here's the way that we would do it, really similar to how we would create a config map. Now, in this case, I'm saying string data so that I can just give the real content. I can also use data, and then I would need a base 64 encoded value. Now, that's great if I have something that will span more than one line, or I really want to obfuscate it. It's not secure, it's just base 64 encoded, but that's the way that I would create a secret with YAML. Now, the whole point of the secret is to keep it out of source control, keep it out of non-production hands. So probably we don't want to create it through a YAML file. Instead, we'll want to create it through the command line. Now, the benefit of creating it through the command line is that we can specify all of these details in one place, and then the moment that command is done, it's gone, provided we clean our bash history. So here we're going to create that secret. We'll give it the name of DB connection, and then we'll do the keys and values. So here's the username, dev user, the password is password. And so we'll be able to enumerate those keys and values that we need inside that secret. Now, much like we map secrets, map config maps into pods, we can map secrets into pods as well. So let's take a look at how we might do that through files. I have a pod definition. Maybe it has other volume mounts that are actual files. Maybe it has other volume mounts that are config maps. And in this case, I have a volume mount that maps to a secret. Now, they are read-only all the time, but in this case, I called that out just so that the reader of this pod definition will understand that they can't really write to that directory. So the application will open up this directory, enumerate all of the files in that directory, and they'll be able to get at all of the keys, all of the secret keys open up each file, and they can get to the secret value. If ever that secret changes, they can re-enumerate that directory, reopen those files, and they'll get at the new values. Alternatively, we can map secrets as environment variables. Now, in this case, rather than just saying all of them are, let's enumerate all of the secrets from that spot, I'm going to specifically call out this name and key. So I've got a DB username environment variable, and I'm going to go grab this name and key from that secret. And so the application can read this environment variable to get at the password that it needs, or the username. Here's the password. So we might choose to enumerate each of the values. We might just want to say env source and go grab all the values, whichever one works for you. So if we need that level of separation, if we need to separate dev from ops, if we need to separate configuration in different environments, we have this mechanism through config maps and secrets to be able to do those Kubernetes specific mechanisms to separate those into different files. If we don't have that complexity in our organization, we can definitely just stick the value of that secret or that configuration straight into our pod definition and avoid that level of indirection. So we've got volumes, we've got configuration, we've got secrets. How would we store data stores? Well, let's take a look at that with a stateful set. A stateful set is a bundle of machines. It creates pods with predictable names and creates a mechanism where we can communicate between those pods. By default, with a deployment, we get random pod names. With the stateful set, we get predictable pod names. So if pod 1 goes down, when Kubernetes reschedules that pod, it will come up as pod 1 so that we know that. Now, the cool part about a stateful set is we can create clusters, maybe a Kafka cluster or an Elk stack or a database cluster. Now, the interesting thing is we're kind of overloading the term cluster here. We have a Kafka cluster, which is a series of pods within a Kubernetes cluster. So cluster, yeah. Cluster now is an overloaded term. Do we mean the cluster that represents this stateful data store, or do we mean Kubernetes as a whole? Maybe as we talk about stateful sets, we should instead talk about all the pods associated with this data store. So we have all of these pods, and here's pod 0, pod 1, and pod 2. And we have this headless service that facilitates communication between these pods. So if container in pod 0 needs to reach out to pod 1, it can do so through that headless service. Now, it being a service, we can accept traffic in and it'll do the standard round robin load balancer across it, but we probably want to create a different service for this. Maybe our internal communication is very different from our external communication for this group of pods. So probably we'll want to have a second different service only exposing the public communication ports. So how do we communicate between these? Let's create a stateful set. Now, if you squint real hard, it looks pretty much like a deployment. The only difference so far is it says stateful set here at the top. We have a selector, we have replicas, we have a template that is a pod definition. Yeah, this pretty much looks like a deployment. The only major difference right here is this service name. That is the name of that headless service that facilitates communication between them. Now, in this case, I've called it DB service, but you can call it anything. Now, as I define that service, what makes it a headless service? We have services that are cluster IP, node port, load balancer. In this case, this headless service, we say cluster IP of none. That's the magic sauce that makes it headless. So we have this headless service, and we have the stateful set that allows us to communicate between the pods within our group. So if we curl to that service, then it will round robin to whichever pod wants to listen to it. But we can also hit the specific pod name dot the headless service name. And now we've gotten to that specific pod. So in my stateful set, I'll have a known quantity of pods. They'll all have predictable names. And now I can do some Raft protocol details of keeping my data up to date by pushing and pulling data between the various nodes to ensure that my Kafka cluster or my database cluster is kept up to date within the Kubernetes. That was cool. We have all of these different resources that allow us to do some really amazing things within Kubernetes. As we take a look now at our diagram of our application, we can start to see how these various stateful resources will really help us build our application to the next level. Now we had an ingress, we had a service, we had pods with containers in them. That's what we had walking in, but we also have some other things. We have a domain. Maybe that's a config map mapped into this ingress. We have a certificate. Maybe that's a secret mapped into our ingress. Now that's great. Here in our pod, we need to connect to a database cluster. Now that database is probably using a stateful set so that the horizontal scaling within this database cluster can keep track of the data that it needs to move between nodes. We have a stateful set together with a headless service. And now we need to authenticate into that. So we probably have a secret baked into our pod definition that allows us to discover where that stateful set is. So we have a secret with the username and password. Maybe the URL is in a config map, or maybe it's part of that secret as well. We have file storage. In our most naive case, we just identify the volumes inside of our pod definition. But if we need to, we can separate that out into persistent volumes and persistent volume claims. We have storage. We break that storage up into persistent volumes. We can claim one of those volumes and we can attach it to a container at a particular URL. So do we need the configuration details associated with how to map that volume in place? We would then separate that into a config map or a persistent volume and a persistent volume claim. Or maybe we just want that to be external storage, in which case we need a path and authorization details. So maybe that's a config map or a secret off into Azure Blob Storage. Now, each of these things, we can see how we have stateful sets, we have config maps and secrets, we have volumes, and each of these allows us to get our application to that next level of being able to get all of those stateful resources into Kubernetes as well. Now, it's been really fun getting to show you all this. You can grab these slides live right now at robrich.org. All of the code that you saw today, you can easily select, paste that into Notepad or your editor of choice, and kubectl apply that into place. Remember that kubectl get all is not going to give you all the resources, but you can enumerate all the resources that you create and ensure that they are in place. For those of you who are watching this video later, hit me up on robrich.org or send me an email or tweet me at rob_rich. For those of you here live in the conference, what are your thoughts? What are your questions? What things should I show next time I do this talk? While we're looking at this, one of the questions that I often get here is, well, how does this work in my cloud? I use AWS or OpenShift or Azure or Google. Will that work here? What's really cool is all the things that we looked at are native to Kubernetes. So any Kubernetes implementation that you look at will have these details.